You're very
again.
welcome. Thank you.
Yeah, and I move to the next presentation. It's by Julius Jurdakis. Are you okay? And the paper is entitled Sound Events Detection Long-Term Recordings Using Changepoints. So it's your time, please. Switch on your microphone, please.
There we go. How's that?
Please start again.
Great. There we go. Hi all. My name's Julius. I'm another PhD student in the avians team in Victoria University of Wellington. And I'd like to talk to you today about a new method for automatic sound event detection using change points. So the problem that we're trying to solve is that we're interested to detect all cues of some target species in a possibly long recording. So here's a short example of a Junko spectrogram. And we'd like some algorithm to detect and mark the two songs visible here for us. Now, modern sound detection methods do this by splitting the sound into windows, possibly overlapping, and classifying each window as having target present or not. So that's how simple energy detectors work, which only use an energy threshold. That's also how spectrogram-based detection works, in which case your windows are columns of spectrogram. But that's also how more complex methods work, like neural networks, which view sub-images of the spectrogram and classify those. In either case, what you get out of this detection is something like this. You get a series of yes-no detections or some continuous probabilities for each window. On average, these can be quite good. Modern methods can do quite well. There will be some parts of the call that get missed due to natural variability. Often parts of background will be marked as false positives due to noise. But on average, modern methods can reach quite good accuracy at this window level. Now, our issue is that for most ecological purposes, we want sound detection to be complete acoustic events, not just windows. So, for example, if we're trying to do a call count based on spectrograms, we'd like the detections to report how many calls were there in these files, not how many windows with some part of the call in them. If we're trying to automatically extract some features from the calls, we also need the detections to precisely mark the start and end of each call. Same goes for human review and for many other ecological purposes. And it seems to us that this stage of combining windows into acoustic events in literature is a bit neglected and often done ad hoc. So we could come up with some simple heuristic here, like let's combine neighboring positive detections into events. And we'll get something like this. But then again, we want more rules to merge the gaps where the algorithm missed something, trim these false positives outside calls. And this quickly gives rise to very complicated pipelines, very complicated workflows to post-process these detections. These workflows are rarely compared with each other, rarely tested how they generalize to different species. So it's really not clear whether they're optimal or not. We asked, therefore, is there a more principled way to do this, to combine these detections into events? Or in other words, can we come up with an acoustic detector that specifically focuses on recovering an accurate number of events at their true positions? Turns out there is such a framework. It's called Changepoint theory. It's been in development in the field of statistics for about 50 years now. And what it says is that if you have some data that looks like this, data that comes from some process that flips between background and event states, and you're interested to detect these transition points, these start and ends of events, what you should do is, first of all, you should test all possible segmentations of the data. So test all possible start and end positions for any possible number of events. and then choose the segmentation that maximizes this cost function based on likelihood and a penalty for the suggested number of events. Now, what took 50 years to develop here? First of all, we now have really fast algorithms that can test this immense number of segmentations very cleverly and efficiently. Secondly, we now have theoretical proofs that following this procedure will lead to consistent estimates. So estimates of number and position of events that converge to the true values. And on this basis, we can propose a sound event detector. So we first propose to wavelet transform the sound. This decorrelates the noise, but it also acts as a filter bank. It decomposes the sound into frequency components. And then we can select the frequency components that we think our target is vocalizing in. So we can choose relevant nodes from this wavelet packet. This is basically equivalent to bandpass filtering. Then we can extract energy corresponding to these nodes and apply a change point detector to this series. So basically, this is a frequency-specific detection of changes in energy. It needs some parameters. You need to train for the nodes and the thresholds, but that's not too complicated and doesn't need too much data. The benefit is that by using this statistical basis, we can say that for white or pink or otherwise relatively predictable noise and sufficiently strong events, doing this process will guarantee that an accurate number of events will be reported at their true positions. So we have the properties that we wanted in the beginning. We implement all these methods, as Alberto very briefly mentioned, in our software Avians. So the software provides a graphical interface where you can view calls, you can annotate them, but you can also apply all these automatic methods that we develop for call detection. So here's a short example. In this really bad quality recording, we have a call of Kiwi, roughly at 3 kilohertz here. And under it, you can even see some faint calls of Morpok, that's a New Zealand owl. So applying our methods to this file is very simple. We have pre-trained 2 detectors for these species. So you just need to select these from the right menus, segment. We have Kiwi detections, choose Morpok, segment. We have Morpok detections. We also have 1 false positive, so these results still need some review, but on average, you can see almost all the events in this file were accurately detected, even the really faint ones. And you can see the start and end marks are really tight around each call, really mark the timestamps precisely. Now, this is a nice individual example, but how to evaluate this more quantitatively? We conducted 2 bird surveys on Kiwi and on Bittern, another bird in New Zealand. Both of them we conduct using this partially overlapping grid of recorders, as shown here. We trained 2 detectors for these bird species using about half an hour of training data in each case. And we also trained 2 comparison methods. They both use the same features, so the same band-specific energy, just different post-processing methods to convert that into events. And now, normally the workflow of processing such survey data is something like this. You collect your recordings, you apply your detector, you get some detections, which you then need to review, filter out the false positives, accept the true ones. And then you can use that into some kind of ecological inference, whatever you want. Now, we use spatial capture-recapture population models, where we utilize this sort of partial overlap between the recorders that we have, so that the model could roughly triangulate the positions of individual sound sources. So this way it estimates the number of sound sources, also the detection function, and from that you can get a density of calls per area unit in the survey area, and also density of animals and the corresponding standard errors. So how would you use that to evaluate acoustic methods, acoustic detectors? Now, one obvious way is to compare the match between the detector output and the expert annotations, sort of ground truth.
Alternatively, you could look at the very end of the workflow and look at the very final inference. And you want to pick the recorder which resulted in the most precise estimates, in the lowest standard error in the end. So in the former case, you would use something like F1 score that captures the agreement between the detection method and the experts. It's simple, but it has various shortcomings. Like it can be easily inflated by deleting half of your data that you pick to be noisy and so on. Precision is a more preferred metric as it captures everything that happened in the pipeline. But we have a whole separate paper on this, so if you want to hear us rant more about this topic, just get in touch. In either case, using the Changepoint detector for event detection was favored by both of these metrics. So it resulted in higher F1 score, better agreement with the expert annotations, but also in the lower standard error of the final density estimate. And if you look here, you can see that some other detection methods, they produce twice worse standard error than the Changepoint detector. So in other words, choosing the wrong sound processing method can be as choosing a better sound processing method can be as good as having 4 times more data in this case. That is how important it is, even though the input features are the same in every case. For an example of a more complex task that could be analyzed this way, there's an acoustic data analysis competition DCase in which one of the tasks was to analyze short YouTube clips recorded in domestic environments. So as you see here, these are relatively very messy files with a lot of things going on. We asked, can we detect cat sounds as an example of a biophonic sound in these files? And the success in this competition is evaluated by F1 score. That's, again, a metric that measures agreement with previous annotations, but it only allows, in this case, 0.2-second time error in the timestamps. So it emphasizes how precisely the methods can mark the start and end of each call. So we trained the Changepoint detector and we supplemented it with a logistic regression classifier. So again, very simple classifier to help us separate speech from other sounds, from cat sounds, from dog sounds present there. We used only 20 clips of 10 seconds for this process, as these are very simple methods. In comparison, the other 50 submissions to this competition were convolutional neural networks, each trained on thousands of clips of data. We'd rank in the top 10, roughly here, among these methods, while using 100 times less annotated data. So this, again, shows that even these advanced methods, they do not optimally use the data. They do not focus enough on the aspect of precisely annotating the start and end of each event. Now, what remains to do in the future here? Our main problem currently is dealing with transient broad spectrum noises, so namely wind. We hope that adding some pre-processing by spectral subtraction could help here. We will then pre-train some Changepoint recognizers using this method for several New Zealand species. But most importantly, we invite you all to try this yourself. The software that we develop, it provides the facility to train these detectors, train other detectors, and also convolutional neural networks for any species that you have the data. You just need, it's all based on a simple graphical interface, so you only need to load your data and you can train anything that you want. The software is free, the software is open source, works on any operating system. Feel free to come by our GitHub where we have all the newest versions of it with the newest features. But we also have a website where we release the binaries, the more stable tested versions that can be installed on Windows easily. We also have example spectrograms for bird recognition and other goodies there. So let us know if it works for you. Let us know how we can help your sound analysis processes, and thank you.
Thank you very much for your kind presentation. We open for discussion about this new opportunity to to investigate animal sound. Are there chat or questions from the panelists or from attendees?
I see one in the QA I can answer. So Vijay asks, why did the Changepoint method perform so much better than the convolutional neural networks? So that is mostly because convolutional neural networks, they view the sound in, they view sub-images of the spectrogram and classify each, but they don't know anything about combining these sub-images into events. So that's really an aspect that wasn't really given enough attention to by the submissions. It was a bit neglected there. So by focusing specifically on that aspect, which was the primarily evaluation goal in that competition, we could really combine even simpler method results into events that are really time-stamped quite accurately.
Other question? Okay, there is another question on the...
Yeah, so Przemek asks, any possibility to have a server command line version of Avians? So yeah, there is indeed a command line version. It's not very well documented, but we're working on that, and we are already using it on GPU machines to do parallel processing, basically. It's very trivial to parallelize, as we just run manually form batches of files to be processed, but it can be run without it can be run remotely over SSH in a command line mode already.
Okay. Okay. There are no other questions. I thank you again, Julius, for your presentation.